Hello, everybody. Thanks for your presence today for the BMP Summit. My name is Lakesh Sharma. I'm a state BMP coordinator in Soil and Water Sciences Department. I'm an assistant professor here. Um, we have two speakers today, Dr. Kelly Morgan. Dr. Morgan is a center director for South Florida Research and Education Center, Immokalee, with the University of Florida. In Soil and Water Sciences Department. Dr. Morgan will present on effect of soil pH on nutrient availability. Our second speaker is Dr. Zach Brym, would present on hemp nutrient management too. So I'll put more introduction on there when Dr. Brym will present. So here we have Dr. Morgan. Dr. Morgan, the floor is yours.
Well, thank you very much. I appreciate everyone attending today and listening. pH is a subject that we're hearing a lot about now throughout the state, and it enters into our recommendations in a very big way. And going through this presentation, I'll show you exactly why we have to be interested in our, excuse me, not advancing.
Dr. Morgan, you may need to unshare. Oh, there you go.
I got it. Okay, so as most of us know, that most crop plants, the acceptable range of pH is somewhere between 5.5 and 6.5, something just short of neutrality. And you can see there that the reason for that is that that the nutrients for plants are most readily available in that range. As you go towards the bottom of the scale, more acidic, lower pH, it's too acidic. The nutrients become bound to the soil in various ways, and we'll talk about that. As you go up in the scale or higher pH values, it becomes alkaline, and the same is true, but in a much different way. So we'll explore all of these things going through the talk today. I found this example of recommended soil pHs for various crops, and as I mentioned before, most of them you can see they're in that upper 5 to 7 range for majority of crops grown throughout the country. There's a few exceptions to that, some that like it a little more alkaline, such as avocado and asparagus, and some that like it a little more acidic, and that's primarily potato. I'll concentrate mostly on alkalinity, and that's the bigger factor in Florida soils, particularly in South Florida. Our soils are becoming more and more alkaline, primarily because of our source of water. But this is true throughout the state, where water from limestone aquifers are used for irrigation. Now, if you're using surface water, this isn't as important, but a lot of our irrigated agriculture is now coming from deep wells down into the limestone, and along with that water comes a lot of bicarbonates, and this makes for alkaline soil, alkaline water, and it causes the soil pH to increase. If your irrigation water is above 7, certainly if it's above 7.5, it's usually associated with bicarbonates. You should have your water tested. Recommended levels are typically in the 100 parts per million of bicarbonates or less if you test your water through a testing labs. The form of bicarbonate salts typically are calcium, magnesium, sodium, and potassium. So you'll see high bicarbonates, but you'll also see high amounts of these 4 nutrients in your water. And as we go through the discussion today, you'll see why this becomes important because the pH of your soil is increasing slowly over time, and you need to bring that back into that productive range of 5.5 to 6.5 for most crops. And there are several ways of doing that, either through applications of lime or gypsum if your soil is too acidic, or sulfur and other acidifying fertilizers if your soil is too alkaline. Just to run through a few of the implications of a high pH. This graph I found on the internet. It was a study looking at the effect of crop height, bean plant in this case, at different pHs. You can see that as you get to a neutral pH, the blue line, the plant heights decrease as through the production cycle. Initially, that's true on lateral spread of the plant, leaf length, and leaf width. The crops just don't grow as well at that higher pH. Some of the reasons for this is that that you have different impacts on your fertilizer components. If you're applying an ammonium source of fertilizer at a low pH, your fertilizer stays in the ammonium form. But once you cross neutrality at 7 and you increase the soil pH, the ammonium turns to ammonia, and that can volatilize through our soils, our porous soils. Our sandy soils allow the ammonia to release into the atmosphere, and you're losing your nitrogen source at that point. So it's not recommended to apply only in ammonium form at a pH above 7. So this has to be taken into consideration with our recommendations. pH has a great effect on the uptake of fertilizer components. In this graph, you can see that the illustration there is of a root. And then if you have an ammonium source, roots take up that ammonium source. It has to expel a hydrogen ion to do that, to balance the nutrients, to balance the charges, excuse me. This is very important. The root must account for its charges. So if it brings on a positive ion, it has to expel a positive ion. So by expelling the hydrogen, it causes the soil pH immediately surrounding the root anyway to go down. If you have a combination of nutrients, such as in panel C there, where you have an anion and a cation, then there's no net change because there's no addition of hydrogen to the soil. If you go down to panel B, where you have nitrate going into the soil, you have hydroxide or carbonates coming out of the soil, out of the roots, and your pH will increase. So what you apply as your fertilizer source has a great impact on the pH of your soil. And that, as we'll see a little later on, will influence how your fertilizer changes your soil. And even going from an ammonium source, as in panel D, from an ammonium source of fertilizer to a nitrate source, which is something that's unavoidable in our soils. There are compounds that you can apply to fertilizer to reduce the rate at which ammonium is converted to nitrate. But in that conversion, you are releasing hydrogen, and that will also cause the soil to acidify. So that brings us to this chart, which is just a very simplified chart looking at the amount of calcium bicarbonate that these fertilizer sources can balance. So you see the blue bars at the top, those are alkaline producing fertilizers, calcium nitrate, sodium nitrate, potassium nitrate. Those all tend to increase soil pH. Ammonium nitrate, urea, ammonium sulfate, those all reduce soil pH. And you can see by the links of the bar, ammonium nitrate acidifies ammonium sulfate acidifies the soil much more than the other two. One of the important things with soil pH is phosphorus. And that's a controversial topic right now as far as our recommendations are concerned. We're using Malic 3 as our extractant for soils to determine phosphorus amount in soils. Because it's an acid, we may be extracting more phosphorus from the soil than is available to the crop plant. And that is illustrated in this diagram. Can you see the my cursor there? This oval represents soluble P that has been applied to the soil. And that is available to the crop plant. That can be taken up by the crop plant in the form of phosphorus. But if you have highly acidic or highly alkaline soils, several things can happen. Over here, you see sorption of phosphorus by clays, which have iron and aluminum oxides associated with them. The phosphorus can absorb onto the clay, and over time they will desorb as the amount of phosphorus in the soil goes down. Same thing for minerals such as calcium and iron and aluminum that are free in the soil. You'll have a precipitation of phosphorus depending on the pH of the soil. And then as the phosphorus in the soil solution goes down, you'll have a desorption of phosphorus from those precipitates back into solution. Typically, the arrow is much stronger towards precipitation than it is for dissolution, but it depends on the soil pH and the amount of phosphorus that's in the soil. And we'll go into those in just a moment. So looking at fixation of phosphorus in the soil, we have the pH continuum down here at the bottom, going from pH of 3 to 9, from acidic soils to alkaline soils. And at a near neutral pH, just below neutral, in the 6 to 6.5 range, that is the highest point at which phosphorus stays available in the soil. So if you apply phosphorus in your fertilizer to a soil that's at a pH of approximately 6.5, it will stay in solution much longer than if your pH is more acid or more alkaline than 6.5. As you go through the pH in an acid soil, the yellow graph here illustrates fixation of phosphorus by aluminum. So as you go down and the highest fixation is at about 5.5, the phosphorus is being fixed by aluminum, either free aluminum in the soil or aluminum that's associated with clay. It's fixed, it's taken out of solution, and it's no longer available until the amount of phosphorus, free phosphorus in the soil goes down. Then you can have some dissociation and phosphorus will go back into solution. If you have soil pH much lower than 5.5 and you're approaching 3 to 4 pH, which is unusual, then your fixation is primarily in the form of iron. Iron very readily fixes phosphorus at these lower pHs, and bringing that phosphorus back out of the precipitate and into into solution is very difficult. The similar thing, but with for a different reason, happens at a higher pH. So as you go from a pH of 6.5 up into the low 7s and 8, you have fixation from calcium. And as the time increases, that pH becomes that precipitate becomes much more solid in the soil and very difficult to go back into solution. This is just an illustration of the same type of effect. You have a 6.5 is where you have readily available phosphates. Then as you go down, it's fixed by primarily iron and aluminum. Manganese enters into that as well. And then you have chemical fixation as you go below 5.5 or 4.5, excuse me. And there, the fixation is much more strong and very difficult to go back into solution. Same thing occurs with calcium on the other end as you go above 7.0. And this is just illustrates that you have a fixation of the H2PO4 that you would be adding to your soil as a form of phosphorus fertilizer. If you have free aluminum, free iron in form of +3, aluminum +3, manganese +3, these will form precipitates with the phosphorus and will become insoluble hydroxyphosphates. And you can see the chemical equations down here below, going from a soluble phosphorus in the form of a fertilizer, along with either iron or aluminum, and that reaction goes to the right and becomes insoluble. Only if you bring this soluble form down does it go back the other direction and become soluble again. At high pH, you have a very similar reaction, but here you have to have calcium carbonate in the equation. So you would have phosphorus in your fertilizer. It would combine with calcium. This compound is soluble, has water associated with it. But at higher pH, where you have calcium carbonate, such as in South Florida, associated with this, it goes to a slightly soluble form and then a very low soluble form. And that's why it's very difficult to go back the other direction just by lowering pH. The other reaction that happens as far as nutrients are concerned with pH is the availability of micronutrients. We've talked about macronutrients so far: nitrogen, phosphorus, potassium, not so much pH related, or sulfur, but calcium and to a lesser degree magnesium are more available in this mid-6 to 7 range. That's where you want to be with your soil pH. But as you look at some of the micronutrients, iron, manganese, boron, copper, molybdenum, zinc, others, if you stay in this pH range of mid-6s to 7, you're at the tail end of their availability. They're less soluble here. They're only marginally available. Their availability is much higher at 5.5, and that's why we stretch the pH of most soils, most crops, down to that 5.5 or 6 range to try to get these nutrients. So even if you're at near neutral, you need to be a little closer to 6.0 to be successful with your crops. Molybdenum is an outlier. It becomes more soluble with high pH, but typically in Florida soils, we don't have molybdenum deficiency issue, except for a few crops. And so this is just a graph of that same information, looking at soil pH. The calcium and magnesium continue to increase as you approach a pH of 7.5. Same thing with nitrogen, sulfur, and potassium. It increases with pH, but never goes low with lower pH. But these micronutrients, that's where the one of the problems are with pH, and why you need to be aware of the pH of your soil. Phosphorus, as we've illustrated, has an acceptable range somewhere in the 5.5 to 7 range, and less available at the extremes. So how does this affect our plant uptake? How does it look as far as what we see in crops? And this is just an illustration of that. Looking at soil pH, they determine the solution of iron from fertilizer in the soil, and as you go down in pH, iron becomes more available. So again, you want to be in this mid 5 to mid 6 range, preferably for these micronutrients. Same thing with zinc. As you go down in pH, you increase solubility. Now, one thing that we have looked at in several crops is how do we treat our soils? And this will assume that the crops are being irrigated from well water, either from drip irrigation in the rows, or micro sprinkler for citrus. And we want to determine how do we treat the water in order to affect pH. If we're not going to look at applications of lime or sulfur to affect those pHs. And what we have found is that if you can acidify your soil, in most cases, our water starts at a pH near neutral to approaching 8 pH. And then if you acidify that water by addition of sulfuric acid or other acids, nitric acid is another one, you can lower that pH to about 6.5, and you affect the bicarbonates in the soil, in the water, and in the soil. So these bicarbonates in the water are reduced, the pH is reduced. We have some citrus growers reducing their pH as low as 3. This doesn't impact the soil greatly, or at the tree. You would think that if you're irrigating with water at a pH of 3 or 4, that you would be causing damage to the tree. But typically our pHs in citrus groves are high enough that in the upper 6s to low 7 range, that neutralizes the acidity of the water and brings that water down to that 6.5 level as it goes through the soil. So the overall effect is to reduce bicarbonates that are already in the soil, causing the soil pH to be above 7. And over time, you can reduce the bicarbonates. The bicarbonates will be reduced to CO2, and it would come off the soil as a gas. And you can reduce that pH, or reduce the pH, from low 7s down to that 6.5 range that you want to be in your citrus grove. So to illustrate that, we did a study on soil pH to look at nutrient status. Here we had a Hamlin orange with an initial soil pH of 7.3. We irrigated with acidified water for 3 years. We had several pH ranges of water from 3 to 6. And the target pH for this was to reduce the pH down to something between 4 and 7. We looked at the amount of the acidification of the water. We looked at bicarbonates, and we looked at soil and tissue samples to illustrate availability of these nutrients, and then finally their effect on yield. We did a survey of citrus groves, and we found that yield of citrus is dependent on pH, strongly dependent on pH. And as you go to more neutral or above neutral soil pHs, the yield declines. And the opposite is true. As you get pH near that 5.5 level, you're pretty well maxing out your yields. So this is why we started the study, to determine how we can reduce our pH, soil pH, from 7.5 back down closer to 5.5. We also looked at root availability for uptake at these different pHs, and we discovered that the higher pHs, pH over 6.5, were all associated with deep wells, water from the aquifer. And those are the well water pHs. So they had a pH between 7 and 8 pH. If you were using shallow wells, not from the aquifer, the pH water was from anywhere from 4 to 5 on the acid side. The bicarbonates, as the water becomes more acidic, there are fewer bicarbonates in the water, and the opposite is true. As the pH went up, there were more bicarbonates. This effect was highly visible on the fibrous roots, the roots responsible for nutrient uptake. We found much lower root mass at higher pH than we did at lower pH. And this was directly related to well water pH as well. So in the study, we had 4 different ranges where we had the pH of the water as it occurred naturally, and that was in the mid to upper 7s. And then we had a target pH of 6 for the water for 3 years, 5 for 3 years, and then down to 4 for 3 years. And you can see that it took a substantial time from January of one year to June of the following year before we got the pH down to our target levels, somewhere down in the 4 range at a pH of 4, and about 5 for a pH of 5. So it took much longer than we thought, but just by acidifying the water to get this reaction of lowering our soil pH. But it did over this 2-year period of time. And just as an example, I have calcium content here. The red bars indicate the optimum level of leaf calcium for citrus. Between these two, optimum would be above this red bar. Low would be between those 2 bars. And you can see we only got into the optimum range at about a pH of 6. As we went lower in pH and higher in pH, nutrient availability was not as great, and we had difficult maintaining optimum pH in our soil. So the conclusion of this talk today was just to look at pH and the effects of pH on our nutrient recommendation. We're all aware of pH. We've been telling growers for years to look at their pH, but we don't necessarily tell them why they need to look at their pH. We can give these examples now to our growers and provide that information to them, that yes, you do need to provide a soil pH in the range of 5.5 to 6.5 to maximize the availability of these nutrients. The ones you see here: nitrogen, potassium, phosphorus, magnesium, calcium, manganese, and zinc primarily. Others as well, iron being one of them. The higher soil pH reduces plant nutrients by reducing water nutrient solubility. Soil bicarbonates are the primary reason for high soil pHs. And by acidifying, either acidifying the soil directly through applications of sulfur or acidification of the irrigation water, you can drive off those bicarbonates and produce a lower soil pH. And then yields increase, particularly in citrus, as you improve soil pH and maintain that between 6 and 6.5. So I'll be glad to answer any questions you may have.
Thank you, Dr. Morgan. We have one comment in the chat box: past recording. Okay, so that's from Emily. We do not have any specific question from the audience. I would request an audience, so if you have any question, please type your question in the chat box and I will ask that question to Dr. Morgan for your answer. I think people might be typing. So Dr. Morgan, I have a question about it. So when the pH changes, the phosphorus availability changes, and there is a on the alkaline soils, it's a calcium, but on the acidic soils, it's mostly aluminum and iron. When it is fixed, does that phosphorus is unavailable for the forever, or it could get back? So is it a reversible or irreversible kind of a process?
But both reactions are reversible. It's a solubility problem at that point. As you go higher in pH, the calcium makes phosphorus less soluble. It precipitates out, but that precipitate can become soluble again if the pH goes down or the phosphorus concentration in solution goes down. It can become soluble. Same thing at low pH. If you have free aluminum and iron, it precipitates out, but then can reverse as you increase your pH.
Thank you. Thank you for this answer. All right, we have a question here. How common is it for the growers to manage irrigation water pH to achieve these optimum ranges?
In South Florida, it's very common. We've talked to, we've been recommending water acidification for citrus and vegetable production for a number of years now. And almost all citrus growers acidify their water, and most vegetable growers do now. They didn't begin with, so this is a relatively new change, but one that they have done just in the past, say, 5 years.
Thank you. Next question is, what is the cost of irrigation water acidification?
It varies on the starting point, how alkaline your water is, but it can vary from a few $100s a year in citrus to somewhere approaching $1,200 to $1,300 per acre. So it can be quite expensive if you start out with very high soil pH and very high water pH. So most growers typically shoot for a reduction in pH down to about 6, because what we found is if you maintain good soil water content at a pH of 6, it doesn't matter so much what the pH of your soil is, because the nutrient availability is then tied into the pH of the soil solution, or the water that's there. If you allow the soil to dry out between irrigations, then your pH could go back up. pH of the solution would go back up, and your nutrients would become less available.
Well, thank you. We have a question on economics. So what is the economics of reducing bicarbonates in water and soil?
What we have found is as you reduce the bicarbonates in the soil, and this can take many years, the soil pH reduces, goes down. So if you start off with a pH in say mid-7s, and acidify your irrigation or directly acidify your soil for a number of years, you can be in that pH range of 6 to 6.5 on a fairly steady state at that point. So you can reduce the acidification of your water, and the cost of acidification would go down dramatically.
Thank you. So there's a question on the quick test. How do you recommend the grower monitor their soil and water pH via lab, or is there any quick, reliable test to determine it?
There are. We have recommended to growers that they measure the pH with a pH meter. You can buy handheld pH meters that are reasonably reliable. Not one you would want in your lab, but one that is will give you a fairly accurate measurement of, say, plus or minus a tenth or two of pH unit, and that would cost maybe $100 or $200. And so we have growers that routinely collect water out of their emitters, their irrigation emitters, after it's been acidified, and take the pH of their water, and they can adjust the acidification injection to their water to get the point that they want.
Okay, there's a follow-up question, Kelly, on the cost of irrigation water acidification. So we have a Charles Shane that's follow-up question. What's the problem being noted by the growers using this method, which means acidification of irrigation water?
I'm sorry, say that again.
So what are the problems being faced by the growers using the method of acidification of irrigation water?
There are a couple substantial problems. One is the cost of the injection equipment can be very expensive because you're injecting an acid solution. So you're talking about stainless steel pumps, stainless steel injection points. So that could be expensive. The other is the solution you're injecting. If you're injecting sulfuric acid or phosphoric acid, they are quite corrosive. That's why you have to have stainless steel pumps. But they can be dangerous to the person applying the acid as well. There are products that is a combination of urea and sulfuric acid. One product name is called Infuric, and it's by adding the urea, it's still highly acidic, but it's safer. It doesn't cause the damage to the skin that some of the acids do, and most growers are using that. Plus, it's a source of nitrogen to the crop.
Great, thank you. Does IFS have any document that gives information about adding acid to irrigation water?
Yes, there's a couple good EDIS documents on acidification.
Got it. Several years ago, horizontal wells were installed for irrigation on flatwood soils. Could they be alternative to avoid high bicarbonates aquifer sources?
we've not tested those, but yes, I think they would be. They would not be getting water directly from the aquifer, and in some of the situations, the farm here on the research site being one of them, we use shallow wells, less than 100 feet, and we don't have the alkaline issue, the bicarbonate issue. If you have relatively shallow wells, you get a reduced flow, of course, because you can't take that much water from the wells at a lower, a lower depth. But yeah, if you can take water from horizontal well, I think that would reduce your need for acidification.
Thank you. Okay, last question. Does this acidification help keep the emitters clean?
It can, yes. That is one side effect of it. What typically happens, the reason you get a lot of clogging is that you'll get these bicarbonates coming in the water, and then they precipitate out at the emitter, causing a hardening or hard deposit at the emitter. That's very difficult to get rid of, but the acidification will cause those precipitations not to form, and can keep your emitters cleaner.
Okay, I think Dr. Dukes actually shared Edith's publication in the chat box on clogging, irrigation, or fertigation. Okay, we can take one more question. How does pH change in well water seasonally or throughout the year?
It does change seasonally, and that seasonally rather, and that's why we encourage the growers to monitor the pH of their water. If the pH goes down, the bicarbonate level goes down, they can reduce the amount of acid that they inject, and the opposite is true. If it goes up for some reason, they need to apply more. So they should have a target pH in mind and try to maintain that target pH. The reason it would go up and down is just because of rainfall. Typically, we see lower acidity and bicarbonates in the rainy season than we do in the dry season.
Okay, we are still getting some questions. We have 3 more minutes for you, Dr. Morgan. I'm thankful to you for answering all these questions, and I'm glad that our audience is asking all these questions. How effective is ammonium thiosulfate in mitigating high pH problems?
It depends on your starting point and your crop. It can be very effective. We have tested that product, and it can bring the pH down half a unit or so, depending on how much you're putting out and what your starting point is. But it can reduce your soil pH.
Dr. Morgan, I have a follow-up question. Is it ammonium sulfate it's been in the literature that's the 4 times more acidic than any other nitrogen source? Would that be more helpful, or people are already using it?
To acidify the soil?
Soils, yep.
Yeah, it's one that is recommended to for high pH soils.
Okay.
If you want to use your fertilizer as an acidifying agent, that's a very good one.
Thank you. All right, we have another speaker lined up. We still have a couple of questions for you, Dr. Morgan. If you hang till end of the session, we would ask you these questions. And now, if you stop sharing, then I will invite Zach to share his screen. Dr. Brym is.
Good afternoon, everybody.
All right, here we go.
That should do it.
Living the dream.
All right. Hey, everybody. So I was asked to come and present an update on the information for industrial hemp and I will come back on several of these resources later on, but just to give you a sense of some of the information that's available, our website and this fertilizer guidelines document we posted to EDIS last year as well. Let's see. So this is as good of a place to start as anywhere. Hemp, as it's defined, is botanically cannabis sativa, so the same plant as marijuana. However, the legal distinction is one of chemistry. So THC, delta-9 tetrahydrocannabinol, must be at a concentration that does not exceed 0.3% to be hemp. So below the 0.3, you have hemp. Above the 0.3, you have marijuana. And so one of these things that hemp farmers are going to need to be concerned about and mindful of is ensuring that their plants do not exceed this threshold. I don't get into that much today, but certainly by way of a definition and the plants that we're talking about here, it's really important. Another distinction to make is the multiple cropping systems and products that can be a result of hemp cultivation. And so I break them down into these three. Each one really is a separate cropping system based on seasonal timing, fertilizer management, harvest, and the like. So fiber is the first one here in the picture on the left. You are putting these at exceedingly high densities. Some folks will tell you 3/4 to a full million plants per acre that you're working to achieve. These fiber plants are harvested just before flowering to collect the stems. The second here in the middle is grain production. So one of the interesting botanical features of the hemp plant is that it is dioecious. There are male and female plants in a population. And so in order to get grain, you want both of those in the field. You allow the males and the female to produce flowers. The pollen, which is wind dispersed, moves from the males into the females and produces the seed on the females. That's harvested as the seeds are hardening. The third cropping system, which generally most folks are interested in modern cultivation, is for flower production. These varieties are high in cannabinoids. So cannabinoids that are not THC, so THC less than 0.3%, but higher in other cannabinoids such as cannabidiol, which is CBD, or cannabigerol, which is CBG. Now, an interesting component of this cropping system is that the trichomes associated with the flowers and the leaves in those inflorescence stems produce the highest concentrations of these cannabinoids. In order to continue producing cannabinoids, you want to avoid pollination. And so the flowers are unpollinated, the grain systems are pollinated, and so it sort of poses an interesting challenge for the hemp industry, with some neighbors looking to put pollen in the air and others looking to avoid it. The cannabinoids are also tend to be transplanted, plants that are clonally propagated and transplanted in the field, and much smaller densities. If they're transplants, you're going to be putting them out somewhere between 1,200 and 2,500 plants to the acre. There are some cannabinoid varieties from seed, and those maybe make a density of 20 to 20,000 plants an acre. So what's the status of hemp in Florida? Well, the commercialization of hemp and licenses to private farmers were initiated in 2020 with the Florida State Hemp Program. These numbers, of course, are already outdated, but this is our sort of summary for 2020. So it was late April that those first licenses were available, and you can see that folks really jumped at that opportunity. By the end of the summer growing season in September, there were almost 600 permits for just better than 500 different businesses, accounting for 13,000 acres. By the end of the year, let's say turn of January, February, this number had already increased, maybe 21,000 acres. Also, reports that I'm hearing from FDAC suggest that maybe 1% of that acreage is actually planted and harvested. So from my understanding, from my knowledge, lots of folks have licenses, but we're still sort of feeling out the acreage that's actually active in the state. I'd like to acknowledge some work with extension folks at IFAS, Matt Smith and Christian Christensen, for helping me collect this information. These are those numbers put out on the map. So we see 500 acres or better per county common in the southern part of the state, and several other counties with large acreages permitted as well, but also sort of not quite ubiquitous. We'll be following up with this information multiple times throughout the year, just so we can keep track. The takeaway is that hemp's here as far as a commercial opportunity. Farmers are getting licensed. Exactly which farmers are going along, planting a crop, being successful with that crop, it's still to be determined. Now, as these farmers are getting set up, getting their licenses, they're also required to be enrolled in the BMPs program through the state. And so I just wanted to take a minute here, and in many ways, hemp is a new crop. Hemp is a different crop to many other of the established crops in the state of Florida, but sort of worth walking through how hemp is the same and hemp's different. So hemp is an agricultural commodity in the state of Florida, which puts it under the regulation of the Florida Department of Agriculture and Consumer Services. And that ultimately puts this crop in any land in agriculture under these BMP mandates. So farmers have to enroll in the BMPs. BMP manuals and guidelines as they come out of the university are expected to be research derived, research specifically from Florida. And along with following those recommendations and guidelines, the farmer is expected to keep records so that they can keep track of what they're doing, and also when the state comes along and looks to ensure that they're operating in compliance to their BMP enrollment, they can do that through the records and implementation verification. So just a couple points to emphasize. It is expected that hemp farmers are enrolled in the BMPs, but there aren't really established hemp BMPs for the state of Florida. We as a university got out with our first planting in 2019, and that was a variety trial, a planting date trial. 2020 came along, our first attempt at some fertilizer research, and you'll see the results of that here. In order to have a recommendation out of the university, you need to have research. And so we're kind of in a chicken or the egg situation. We do have some guidelines that are out based on research from other states, but this is an ongoing and important sort of situation to keep up to date on as the research out of the university continues to get established, as our information continues to get out there. So it's really important to be working with your FDAC's agent on your enrollment and be thinking about these really basic principles in order to be appropriately managing your nutrients on farm. So these are the 4 R's. You'll see these in the vegetable manual and the citrus manual. Really, anytime someone's working to describe best practices in fertilizer management, we're talking about these 4 R's. So the right source, the right rate, the right time, and the right place. At this time, these are sort of the best approach to fertilizing hemp, just by being mindful and ensuring that you're being a good steward of that environment of the water quality. So just because this is such an important topic, I wanted to take an extra moment to describe some of these things. So the source, you can ask yourself, is it best for my farm, best for my environment to come from a synthetic source or an organic source? That'll depend on your farming system and your long-term goals for your farm. If the source of fertilizer is going to be a single compound, for instance, nitrogen, or if it's going to be compounded across multiple. So you'll commonly see fertilizers that are mixtures of nitrogen, phosphorus, and potassium. There again, based on your system, based on your crop, you'll ask yourself whether or not it's best to apply as a dry source or a liquid source. So we don't necessarily have a whole lot of answers specifically for hemp about how to be doing this currently, but it is important to be thinking deeply about these issues so that you can do best for your farm. The others, the right rates, right time, right place, these are all very similar considerations in terms of how to ask yourself these sorts of questions. So what is the fertilizer, what is the nutrients existing in your soil? So can you account for the nutrition in your soil, for the organic matter in your soil? How does this relate to the plant growth? So it's probably not a good idea to be putting on a whole bunch of fertilizer months before your crop goes in the ground. It's going to rain and the fertilizer is going to be leaving the soil before your plant has a chance to take it up. So making sure that you're timing that up. Small plants probably need less nutrients than big plants that are putting on flowers, for instance. And another sort of aspect to be considerate of. Also, of course, these things will change by season. The dry season is going to be a much different scenario than the wet season. And I mentioned it several times, the cropping system that you're choosing. Nutrient management is going to be different in a fiber system than it is in a flower system. So just to like summarize and to sort of put this on the nose for what a good 4 R's in the hemp space with the lack of information that we're dealing with these days. Be aware of your crop, be aware of your farm. Take extra time to reflect on the nutrient management. I'll go through some information that you can draw from in that reflection. You could also do it by observing your plants and how they respond to very different nutrient applications. Definitely can't hurt to go slow with a little bit of land as you're getting started in the industry. And as a data scientist, as a scientist who's interested in information and record keeping, of course, I'm going to say keep good records so that you can reference them, but they'll also be critical in having a good experience with your FDEX inspector. So we were able to put something together based on existing research from around the world, not from Florida, but from around the world. And I'd like to recognize my co-authors on this document, Rao Milavarapu, graduate student of mine, Luis Monserrate, and collaborator Michael Mulvaney. And so what we did was a broad literature search of hemp nutrient research historically, and we also reached out to folks in other state analytical soils labs to see what their recommendations were in those states and kind of how that might inform our approach to Florida. So to be very specific about the words that I use here, these are our guidelines. This is a report of our findings preliminarily. We are working on the research that would end up being sort of more appropriate as a recommendation. So just to read through here, the slides, nitrogen, not to exceed 150 pounds of nitrogen per the acre. This is something that we have seen in the research that I'll show you, but also if you over apply the nitrogen specifically for fiber crops, for instance, we've seen that the hemp crop will take up extra nitrogen. They call it luxurious uptake. It'll take it up and it won't benefit the crop. In fact, in terms of fiber quality, too much nitrogen will actually reduce fiber quality. We've also seen a couple indications that too much nitrogen can reduce the cannabinoid development as well. So back to that point about nitrogen, you probably don't even need 150 pounds of nitrogen for fiber crops. As Florida tends to be sandy and low organic matter in nature, water passes through the soil very quickly. We recommend that these nitrogen applications are done in split applications so that you can spread out across the year and make sure that the nitrogen you are applying is going to the plants. Phosphorus, this goes back to kind of being aware of your soil, accounting for what's there. We definitely recommend soil tests so that you can see what's there. The guide helps break down soils into low, medium, and high phosphorus. And the guide, as it's published, recommends somewhere between 0 and 125 pounds of potash per the acre. But really, what we've seen from the research is something in the middle, somewhere between the 20 to 70 pounds of P2O5. Potassium, something similar. Again, test your soil, know what's in there as background rates. What we were seeing from the research and from other states is somewhere between 0 and 100 pounds of K2O. Probably something more. So potassium is probably something that hemp does need in a reasonable rate. So the 65 to 120 is what we are seeing there. Just again, to emphasize a couple of these caveats based on this report from 2020, all of the research and information that we gathered for this report was from outside of Florida. So we're working really hard to get that information for Florida. Also to point out that the abundance of research out there on hemp fertilizer is primarily for grain and fiber cropping systems. And so we're still working to catch up on the flower systems as well. So the rest of this talk is just to kind of go through, give you an idea of what we are working on here at UF-IFAS for hemp nutrient management. This study was started last year, 2020. This is here in Homestead, so very calcareous, gravelly soil, pH somewhere around 7.5, just to link up the comments from before. So we didn't change the pH in the soil, but definitely a reason to acknowledge that it's a single site, a single year so far. This was a cultivar called Weiss that we transplanted out into the field, and we put on 6 different nutrient applications from 0, 50, 100, 150, 200, and 250 pounds of nitrogen per the acre. And as you can see from the picture in the right, we did have some differences that we saw in the treatments. And so, as I mentioned, the fertilizer guideline document suggests not to exceed 150 pounds. And we saw that in our research last year, that there was no benefit to hemp biomass, the total mass of the plant, by exceeding that 150 pounds. So 100 might be good enough. Probably want to get closer to 150. Again, these are just in the Rockdale soils here in the Redland of Homestead. But this sort of information is what we're looking to collect. I am working with Mike Mulvaney, Lakesh Sharma, and Django Vada on a project sponsored by FDAC's Office of Ag Water Policy, and 3 locations, Homestead, Citra, and Jay, are going to be doing a similar study to this one here this coming year. And so we'll be able to collect this information for multiple sites and ag environments across the state. I did also want to show this graphic. I think it's fun. I think it's a direction that we'd like the research to go through. I was working with a group, Cultivate AI, out of Orlando. They flew some drones, aerial-based imaging with the drones, and these images here are false IR images, and so having the opportunity to calculate a vegetation index that uses a red and near infrared bands of light in order to do that. Just the takeaway message here is that what we're able to do is capture differences in plant health that are associated with the nutrition. So in addition to the size of the plants lowering, we also saw a difference in the vegetative index. And so the plants that were more healthy, so that 150 pounds of nitrogen, also we were able to capture that from these aerial images. So stay tuned for some more of this work as we expand the program. As I mentioned, expanding the multiple sites, we installed some soil sensing equipment across the sites, so some drain gauge lysimeters out in the Citra location. We're also expanding, so that one trial, the pilot trial last year was just the flower system, but we're including the grain and fiber systems as well in the study. So thanks to the folks at Ag Water Policy for supporting the work, and I'm really excited to have a go for the next couple of planting seasons at collecting this information. So Luis Monserrate, my graduate student, was able to do a study in the greenhouse as well. And so this is a container study where he changed fertilizer upon flowering. So this is more a fertilizer supplementation. So these plants were maintained similarly up until the experiment. And then sort of at flower, he changed this NPK at a consistent ratio at these different rates, 100, 200, 300 parts per million of nitrogen. And we do see sort of increasing biomass for the increasing fertility, but not necessarily a statistical increase after the medium. So again, these plants will take up luxuriously the nutrients, at least the nitrogen and potassium that we give them, but that doesn't mean that there's going to be improvements in the yield. So this medium, the 200 part per million, at least from this one study, is another indication for supplementing fertility at flowering. Interesting point to make here. This is Luis separating out his plants into stems and leaves away from the flowers. And so the nutrition could also change the biomass partitioning here, where the stems and leaves actually are more expressed in higher nutrient rates than the flowers. So again, more nutrients, more fertilizer does not mean more flower. So if you're going after more flower, if you're going after fiber quality, it seems to be that a more moderate approach to fertilization may not crank up your biomass, but it'll improve those qualities. This is work done from the Mid-Florida Research and Education Center. My colleagues, Steve Anderson, Brian Pearson, and Roger Kellgren. Really interesting work that they were able to do in a controlled environment. And so this scenario was one where the plants experienced a fertility rate consistently, so they continued to flush out the containers and make sure that these plants existed in these conditions from the 50 ppm to the 600 ppm, and the pictures tell the story themselves, right? That those lower nutrient rates the 50, which is the line in gold or mustard yellow, tends to have better growth and better outcomes than any of the greater fertility rates. And so just another way to show that we can be moderate in our fertility management for this crop. This is another outcome from that same study where the total potential CBD, cannabidiol, and the total potential THC do not sort of elevate with elevated nutrients. And again, in fact, the opposite, that 50 ppm with the higher concentrations of cannabinoids. Now, whether or not these rates and declines are due to plant health, you know, there's a lot of additional questions to ask, but some interesting preliminary results. You should notice that this figure puts a dotted line at the 0.3, and so this is something we have been seeing across our trials at the university, plants regularly going hot or exceeding that 0.3% THC. So farmers, hemp farmers, you're considering hemp farming, make sure you're taking those cannabinoid tests regularly and harvesting appropriately. Harvest at the right time is one of those things that folks are concerned about. Definitely something makes me cautious to acknowledge. So just to summarize where we're at so far with the hemp fertilizer research here at UF, the early evidence seems to agree with the research that we collected from outside of Florida. 150 pounds of nitrogen per the acre, certainly not to exceed that. I've said this multiple times through the talk, more does not mean better. And so again, be aware, you know, try some things, keep your records so that you can see what's working for you. I mentioned that nutrients can impact the cannabinoids. We also saw that nutrients can delay flowering. So more nitrogen than the 50 pounds to 100 pounds and greater may have pushed back flowering as much as 2 weeks. In the highest rates as well, that 200 and 250 pounds of nitrogen out in the field in Homestead, we saw manganese toxicity. So that was an issue that we saw in our trial. Luis also saw some micronutrient deficiencies in the greenhouse study. So we're collecting leaf tissue samples in our studies so that we can follow along plant nutrition with the fertilizer applications. So with just the last couple slides, I'd like to acknowledge the resources that we do have available. This is the website for the UF Hemp program. I welcome you to visit. We're going to be continually updating our resources page for the upcoming cropping season. Actually, today was our first planting date down here in Homestead. We got a planting date trial in for some grain varieties, so that's really exciting, and we're happy to go along with the farmers this year and make sure that they have the best available information available to them. And if you're interested in what the UF Hemp program's been up to, we put together this virtual workshop. It's reporting from our 2020 year, but it's available now on demand online through November. So come along and join us. There's over 20 researchers and extension agents and students that have put up information to share with workshop participants, and we'd be happy to engage you with the dialogue and have you along in the workshop group. So if you do have any questions, you're welcome to reach out, hemp@ifis.ufl.edu. Check out our website, come join us on the workshop, and with that, I will take any questions.
Thank you, Zach, for your amazing presentation. I will request audience, if you have any question, please type your question in the chat box. Emily, could you be able to put the QR code on the share screen, and also if you can share the survey. Audience, we have a very short survey, less than a minute for you to fill out. It will help us improve our programming, delivery, and other aspects of extension. Please fill that survey. Emily, if you have that survey link in the chat box, that'll be great. For the QR code, you can see screen very soon to scan that QR code. Okay, so all right. Michael has a pretty amazing question. How many jokes you have heard, Zach?
Yeah, I mean, all the time. They're hempening all the time, you know, the hemp jokes just are endless. You know, especially when you start telling folks that some of your crops have the tendency to exceed that threshold. So yeah, we're having a lot of fun.
Great. So if you have any question, please type that question in the chat box. I think Dee has asked Kelly if Kelly can help, and I think Kelly already replied to that he will be able to help Dee with her project on peanuts, by pH bicarbonate study in peanuts. So I think that's already addressed. Thank you, Dr. Dukes, for sharing EDS publications, hemp fertilization, current knowledge and gaps and efforts in Florida, 2020 report. Okay, we do not have any question at this point, but I think some of the audience is filling up the survey that we have a link shared in the chat box.
I could ask a question.
Go ahead.
So Zach, thanks for that presentation. Talk a little bit about, if it looks like that rate's going to be 100 to 150, talk a little bit about different production systems that you might imagine seeing throughout the state, you know, South Florida versus Apopka versus maybe even if growers want to grow hemp under center pivot. I don't know if that's a thing, but if they did, how would that affect, would you imagine, the fertility?
Yeah, well, one of the things that we haven't done well yet is to be able to compare the granular rates with the fertigation rates. And so I expect that to sort of be a balance for the program. One of the things I'm really keen in doing is the grain cropping systems, but also to be able to compare that with the flower systems. So let me say that in a different way. It's likely granular in the more agronomic crops, grain and fiber, but we're seeing preponderance of drip, irrigation, and fertigation in the systems for flower on the raised beds, under the plastic, et cetera. And so, you know, sort of learning about what the plant needs and then being able to modulate those needs to the various different irrigation systems. I think that's a really important point, notwithstanding the different pHs across the different trial locations. Plant density. I mentioned 1 million plants an acre for the fiber. Now that's something for folks that are on grain drill are really can expect that their seedlings are going to get out ahead of the weeds. Not another hemp crop, you know, the crop. Anyways, there's another joke for you. These are wimpy seedlings. And so there are several other folks that are putting it on the grain and the fiber on 36-inch centers. And that allows them to bring the cultivator through the rows. And so, you know, there's a whole bunch of options for cultivating hemp. And of course, we're supposed to come up with a single answer by way of a recommendation. But, you know, we're still, speaking as kind of an industry, the hemp industry is still working on kind of what's the best cultivation methods. what are the genetics, right? How's fertility going to change based on the different genetics that we bring into the state? That's a whole nother something. Based on the genetics, your cropping system can be something between 35 days and 100. So your fertility management is going to be different just by the length of your cropping system. I don't know if that's what you were looking for from an answer, but that's what comes to mind.
Thanks.
Okay, Zach, we have a question here. Are there markets for these hemp products now, like seed, fiber, and flour?
I'd say that is a very important question that any hemp farmer needs to answer before they go and plant a whole bunch of acreage. Right now, it's another chicken or the egg situation. There kind of has to be hemp out there for someone to want to buy it. We saw a couple large processors go out of business in 2020, processors for flour and cannabinoid extracts, processors for fiber and grain. And so there's kind of a glut of material out there that should have been processed in 2020, but it's just kind of sitting in barns waiting for their turn. So I'm very cautious to say that there is a market. I think there is a growing awareness of hemp products. You see them in the grocery store. You can buy whole hemp seed. You go to the gas station or the grocery store, there's CBD products. So the products are out there. The remaining question is, what's the pace of raw material production, processing, and consumption? And so that's kind of what we're waiting on. And I won't say emphatically yes just yet. We've also seen some prices drop.
Wow. Okay. Thank you, Zach, for answering that question. We have another question. What are the farmers advised to do if their THC9 exceeds the limits? Burn, bury. Also, what does the research say about volunteers?
Yeah. So there's very specific language out of the USDA for termination. So maybe I should, if your THC exceeds, then as the language stands in the state of Florida, you have to destroy. There has been a move by the federal government to allow for mitigation, and that's something that can come along as well. I'm not aware if that's been allowed for the 2021 crop. If you are to destroy, this is another one of those hemp jokes. If your hemp exceeds 0.3% and it's hot hemp, right, one of those acceptable destruction methods is to put it in a pile in your field and burn it. Right. The remaining question is, how far away from that pile do you stand? You can also disc it in. That's sort of digging a big hole and putting in the ground. There is a USDA document that basically gives all those acceptable policies. They are collecting and burning on field, collecting and burying, terminating and incorporating. Those are sort of pretty logical things. If you do have grain production, there can be pollination of flower crop that exceeds 0.3%. If that does happen, its seeds end up in the ground. We have shown that seeds that are left or abandoned or dropped do come up as volunteers. So one of the things we did in our trials from 2019 was let some of the grain crops seed and shatter. And then we just left that field feral for now we're 2 years in, and those seeds continue to germinate and emerge from the soil, those volunteers that you mentioned. We have also disked a field with under those conditions, and seeds have still come up. So in addition to being mindful and aware of exceeding the 0.3% THC and ostensibly having an unmarketable crop, a crop that cannot comply with legal regulations, there could also be the instance where the volunteers come up in the following year. So that's a great question on both sides.
Zach, I have a follow-up question with that. So if a farmer has more than 0.2% THC, and the farmer has to either bury or burn the crop. Is there any insurance policy or some kind of, is there anything that a farmer will be compensated for it?
Out of Florida, no. So there are some federal programs that have become available to hemp farmers, but those are kind of all crop scenarios. So there is, to my knowledge, there isn't a specific hemp crop insurance program. You can incorporate hemp into a whole crop insurance program. Now, one of the things that those insurance programs require is a record of commercial cultivation in your state.
Mm-hmm.
So 2020 was the first year, so those insurance programs will have to catch up with the information from Florida. So states that had earlier pilot projects, had some form of commercial cultivation in previous years, they have the numbers collected for those insurance programs, and we're catching up in Florida as well. So yeah, I mean, that's a whole nother talk that I give, all the risks and challenges associated with hemp cultivation, and I'm really glad that many of them came up during our discussion today.
Okay, very good. Dr. Morgan, you are invited, and we do not have, okay, so do you want to answer the question for the last question from D. Broughton? Dr. Morgan, are you there?
I'm here, yes.
Yeah, so there's a question from D. Broughton about some study she's doing in peanuts, use bicarbonates in peanuts, and I think you replied. Do you want to elaborate that a little bit?
Yeah, I'd be glad to discuss any project with anyone. Just give me an email and we can plan a meeting, and if you have any questions about pH, I'm glad to answer them.
Awesome, thank you. All righty, so we do not have, okay, Zach, to everybody. Oh, that's you. Okay, great. All right, I would say thank you to both speakers for these amazing presentation, Dr. Morgan and Dr. Brym. Thank you for being present and for this amazing information that you have given to us. We will share the survey results with you once we have those. Thank you, Dr. Dukes and Emily, for helping organizing this BMP Summit. Our next week, I believe, is we do not have any session next week because of a conflict with another extension program. So we will meet now on May 11th. So we'll see most of you on May 11th for our next session. And I think I'm the presenter for some sensor work there. So we'll see you then. Thank you, everybody, for being present today. Take care.